Alright, so section 7 deals with the fundamental theorem of algebra. And with the fundamental theorem of algebra says, if f of x is a polynomial of degree n, in other words, some polynomial with some sort of degree, like 3x to the fourth plus 2x squared plus 3. Okay, and n has to be greater than 0, so our n is 4. Then the equation f of x equals 0, so if we set this equal to 0, has at least one solution in the set of complex numbers. In other words, there's at least one solution that could be real or imaginary, but at least one solution for this guy. And the corollary to that is, if f of x is a polynomial of degree where n is greater than 0, then the equation f of x equals 0, so it starts off the exact same, has exactly n solutions. So we would say that this guy has 4 solutions if we count each repeated solution as 3 separate ones. And so that's what we're looking at for this guy. So how many solutions then, just using this, how many solutions does the following equation have? Well, go ahead and look right here. That's going to tell you how many solutions you've got. And so this guy is going to have 3 solutions. Okay? And if you want, you could graph this and look for x-intercepts. And if you can find an x-intercept, you have found a solution. Alright, how many zeros does the following equation have? So we're looking at this guy down here on the bottom. And again, we go to the degree of the polynomial, and this guy's going to have 4 zeros. In other words, it crosses the x-axis 4 times. Now, they could be real, or they could be imaginary, but there will be 4 zeros for this problem. So that's all there is to it. Look for the degree, and once you find your degree, that's the number of zeros that you could get for that particular problem. Okay, so we want to find all the zeros of this polynomial, and it's a long one. And when we do that, we're looking for the degree. We need 5 zeros. Okay, so we're going to look for 5 zeros. And the easiest way to get started is to graph this guy. So open up your graphing calculator, and let's go ahead and graph. Let's see here. Let's go ahead and graph the problem, which would be x to the 5th and minus 4x squared Alright, so we're punching all this in. And we're going to try and figure out, after we do this, what our zeros are. And if we can figure out some of our zeros, then what we can do is synthetic division. And with that synthetic division, we can get our problem down to something that we've been working on. So I've got a 5th degree equation. I need to find 5 zeros. So let's capture this guy and paste him here. That's not it. So let's copy this and paste it. There we go. So here's my graph, and when I'm looking at this, I have a 0 right here, and I got one right here. And so what I'm going to do is I'm going to use my synthetic division. I've got one at -1, it looks like. So let's do some synthetic division. So -1. Whoa, that's a 5. That's a gross looking 5. -1. Looky here, it's going to work out. We get 0. And since it bounces off the x-axis like this, that usually indicates that you've got a number that can be used more than once. So let's just try 1 again and see. If it gives us a remainder of 0, it works. If it doesn't, no problem. We'll sort it out in a minute. So again, with the synthetic division, and looky here, it works out again. So we've got 2 of our zeros now. And then let's check this guy. Looks like 2. So 2, -8, 7, 14, 0. All right. So this is excellent. We've got ourselves down now to we've got 3 of our zeros. We've got 2 more to find. -1 gets used twice. 2 gets used once. And so now I've got x squared minus 4x plus 7 equals 0. This isn't going to factor, so we just use our quadratic formula. And x equals the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. And so what we're going to end up here with is 4 plus or minus the square root of 16 minus 28. 16 minus 28. That sounds like -12 over 2, which is 4 plus or minus 2i square roots of 3 over 2. Again, if you've got that negative underneath the radical, that becomes an imaginary number. And if you reduce 12 with a factor tree, you have a pair of 2's that you can take 1 out. So what then are all of the 5 zeros for this problem? All of my 5 zeros are -1, -1, 2, and then 4 plus 2i square roots of 3 over 2, and 4 minus 2i square roots of 3 over 2. So it's kind of a long process, but it's totally doable. Just got to be patient. And if you get a negative number under the radical, that is okay. Okay, so the last thing that we want to look at in this section is writing a polynomial function f of least degree that has rational coefficients. So we want rational, which means we want numbers, and with those numbers we also want the leading coefficient to be 1, and then we want 3, and 3 minus I is 0. So here's my 2 zeros that I'm given. So when we start working this thing out, we've got to figure out like what the zeros are, and I've been told that x is equal to 3, and that x is equal to 3 minus I. Well, with radicals or imaginary numbers, all those zeros occur in conjugate pairs. So if they tell me that x is equal to 3 minus I, then x equals 3 plus I will also be a possible solution. And so what I'm going to do is I'm going to rewrite all these so that they equal 0, and it's not going to be like a fancy thing. But it's going to look like this. and here's all my zeros. So I might go in reverse. And what's going to happen then is I'm going to look at all of these as factors. And if all these factors equal 0, then to get a polynomial, I just multiply these factors together. And then, when you factor these guys out, always do the conjugate pairs first. Because when you multiply these two guys together, well, that's awesome. When you multiply those two guys together, if you do it correctly, the i's will cancel out. So, just FOIL these things out. Well, it'll be hard to FOIL. But just multiply these guys out. Everything in the front times everything in the back. Everything in the front times everything in the back. So we're just going to leave the x minus 3 alone. But we're going to have x squared minus 3x minus ix, and then minus 3x plus 9 plus 3i, and then plus ix minus 3i, and then minus I squared. So clean this guy up. He's really long and nasty, and again, we're not going to worry about that front one. So that's just going to be x minus 3. Well, Windows warning. So minus ix plus ix, they go away. Okay. Minus 3i plus 3i, they go away. Alright. X squared doesn't have anybody to go with, so he goes there. Negative 3x minus 3x is negative 6x. And then don't forget back here, I squared is negative 1. So at the back, I'm really looking at a plus 1, which means that my plus 9 and plus 1 go together to give me a plus 10. And so just pay attention on this and notice that I have no more i's left in my polynomial. So when you multiply your conjugate pairs together, and your conjugate pairs are these two guys, you know, highlighted in blue. Once you multiply those together, the i's will go away. And then all I need to do is multiply out the first term with the last term again. So x cubed minus 6x squared plus 10x, and then minus 3x squared plus 18x minus 30. And so now apply things that are common together. They go together. And so I've got x cubed minus 9x squared plus 28x minus 30. And that's it. That's all you have to do to combine your polynomials down. So again, it's a long process. It takes a few steps, and there's 1,000 places to make little mistakes that can lead to your doom. But there's some good checkers along the way. And one of those checkpoints that you just need to be aware of is after you FOIL out your conjugate pair, your highlighted pair in blue, all the i's should go away. If you still have i's left over, then you're going to have an issue, and go back and double check your original setup.